Okay, so hello. I think I've made one blunder that I recorded this whole session by writing freehandedly, which I like. But the thing is that the audio was recorded, but the video was not, thanks to OBS Studio. So I'll just go through what I have written here, and then let's see how it works out. So I was in the topic of this video is to define the four vectors to illustrate what the four vectors are, why do we need them, and special relativity. So we start with the 3D vector. So 3D vector, as we know, it is just a arrow, right, in 3D, and we can define a unit length here, and then collecting those unit length, adding them up, we can simply make a finite length vector. And the a vector in 3D is written as the magnitude of a times the direction at which it is pointing. So it is pointing in this direction. But the idea of vector is mainly illustrated when we change the coordinate system. So this is one particular coordinate system. This is another coordinate system. This is S frame. This is S prime frame. And this S prime frame is basically rotated with respect to the X frame with angle theta. So we see that in this rotated frame, the vectors don't change, and that is very intuitive because the points O and O prime here, they are not changing, and the another point, it should not, the existence of points should not depend on the choice of the coordinate system. So the distance between these 2 points O and P, they should also not change even if we have changed how our axis look, like now they are tilted. So mathematically we can represent this A vector in this S frame as AX I cap and AY j cap, and in the S prime frame we can represent the same vector because the vector doesn't change as AX prime I prime cap plus AY prime j prime cap. Now we can using some simple trigonometric rules which you can obviously figure out yourself, AX prime and AY prime can be written in the matrix form as this particular relation here because it depends on the AX and AY. That's how you transform. So this is a transformation matrix. This matrix in the box here, I should probably change the color. So this matrix here, this is a transformation matrix, right? Sorry. Yeah. So this is a transformation matrix right here, and this is a linear transformation matrix because it is a linear combination of the old AX and AY. Similarly, the I cap and J cap prime, they transform in exactly the inverse. This matrix here is the inverse of the above red matrix. So this pink matrix here, or the magenta matrix here, it is the inverse of that red matrix, and that's why when, because they have to be inverse, because that's how they will counter the transformations here and then keep the vector intact. Okay, so that is the whole point here. That was the whole point. So okay, so enough of 3D vector. So from the 3D vector we have the notion that the vector doesn't change, and if our coordinate, the vector doesn't change with the coordinate system, but when the coordinate system changes, its component changes, and then we have a transformation law for that. So that was the motivation to introduce the 3D vector. Now for 4D vector, because we know that in the special relativity we have four dimensions. Time is also a dimension, so we have to treat that dimension also inside a vector. Okay, so this is something I wrote. This is a Lorentz transformation. So this equation here is a Lorentz transformation, right? Which we have seen in the video number 2. And this matrix here, this is also a Lorentz transformation matrix. So this matrix is called Lorentz transformation matrix, right? Which is very clear. So it is very similar. Like here, the prime components are here, and then this is a matrix, transformation matrix, and the old components are here. Okay, and the gamma is defined as this quantity is Lorentz scale factor, and the beta is V by C. Now the next quantity which I am going to define is the proper time. So what is proper time? So in order to completely grasp the proper time, the let me set up the coordinates here and who is measuring. So we have a frame X, Y, Z and CT here because I am not showing to declutter, I am not showing Y and Z axis, but imagine they are there. So it is really 3D. It is really 4D because now the CT is also there. So time here is already is being treated as a dimension. Okay. So now this part there is a particle. So this is a trajectory of a particular particle where it goes like this in particular zigzag pattern. This particular trajectory, when it is seen in the four-dimensional space-time, it is given a different name, which is called the world line. So this particular green trajectory here, this is a world line. And we are saying that the particle also has a frame, and that frame I am representing as S prime frame. So S frame is this particular frame in which we are seeing the particle is moving, and when you go to that particle, that frame is S prime frame. So what is the proper time here? So proper time is the time measured by the clock in the particle frame. So let's say that when the particle goes through this point and this point, so there will be some time elapsed in the particle's clock. Now that time elapsed is called the proper time d tau. So now what we can, we are really, so what we are interested in? We are interested in calculating this d tau with, given that we know dt, dx, dy and dz, right? Because the particle is moving from here to here. There is a change in coordinates of the particle, which is c dt, dx, dy and dz. So we want to know the time elapsed d tau, proper time, with connection between d tau and these quantities, okay, in the string. So we'll just use the space-time invariance here, which is this c square dt square minus dx square minus dy square minus dz square is equal to c square dt prime square and everything primed here, right? Now the idea to measure the proper time is that, imagine here the thought experiment was, this is the my s frame, this is my s prime frame. The s prime frame is moving in a car. It is a very good car, Mercedes Benz, and then there are two trees here on the line, okay, on the road ahead. Now this S frame is, can see that trees are static, but the car is moving, right? And with respect to S prime frame, the car is static, but the trees are moving towards him, right? That's how the relativity works. So I am I am defining the interval when this these trees are called T1 and T2 here. So there are two trees. So when the trees are aligned with the front end of the car, so initially the car was here, the trees are somewhere like far behind, far ahead of the car. So when the car will move, surely there will come a point where the first tree will be aligned. This is that case when the first tree is aligned with the front end of the car, and then there come a second point when the second tree will align with the car. So I'm defining the events like this. So see, dt is, what is dt? So dt is the time elapsed between when the two trees are aligned with the front end of the car. So that is how dt is. And what is dx? So dx is basically this distance moved along this x direction, dy in y direction, dz in z direction, if you imagine in 3D. But the, like that, it is just the it is just the component distances between these two events. That's all. But what is happening in S prime frame? That is more interesting. So in the S prime frame, the car is static, but the trees are moving. So which is being illustrated here, that the car is static and the T1 and T2 are moving. So where are the two intervals? So the two intervals will be when the first T will come here. So this is the first interval. Okay, first interval, I mean, not interval as the first event, and the second event when the second tree will be aligned with the car's content. So this is the second event. Now, in the both of the events are taking place at exactly the same spatial location when measured in the S prime frame. So I'll repeat myself. In the S prime frame, the events are happening at the same spatial point because the spatial point is fixed, and that is the front end of the car. So we can simply put dx prime, dy prime and dz prime equal to 0 because there is no spatial distance between the events, right? So now we can simply write this particular, I will use a different color here, this space-time invariance thing and we'll put dx prime, dy prime, and dz prime equal to 0, and dt prime is simply d tau, because that's how we define that it is the time measured in the moving particle frame. Okay, so this is how we can write doing some algebra. We can write this here. What I have done is, in this step here, I've taken out the dt, and then it became dk dx by dt, dy by dt, and dz by dt, which is just the velocity of the particle. So it is the velocity of the particle which I am representing as u, and I have written here that u is the velocity of the particle. Didn't I write that? Okay, I'll write that here. U is velocity of particle measured in a frame. What is d tau? D tau is the time measured by moving particle. And what is dt? Dt is the time measured by the S frame. Time measured by S frame in the S frame, right? And the d tau is the time measured in the moving particle frame, right? So yeah, so that is the idea of the proper time, and this equation here, this simply illustrates that if there is nothing special about the S frame, even if we are watching the same particle P with respect to some S double prime frame which is moving with velocity v, then the same relation will hold. D tau will be dt double prime and u vector double prime, where u vector double prime this time is the velocity of particle with respect to S double prime frame, right? And this relation will hold. So what we can see here is that it is very much intuitively clear now that d tau should be frame invariant, because it is simply the time measured by the particle itself. So it should not depend on from which frame we are watching that particle, because it is measured by the clock on board of particle, right? So now next thing is we can use this invariant quantity d tau to define our four vectors. How do we define four vectors? It is very simple. This is ui upon d is equal to dxi upon c d tau. So this is a dimensionless number because this has distance unit and this has distance unit. So it cancels out, hence it's a dimensionless number. So u0 will be c dt by c d tau. U1 is dx upon c d tau, U2 is dy by c d tau, U3 is dz by c d tau. From this definition I'm writing. Now, just now we have solved for we have a relation for d tau in terms of dt. So we can simply plug this relation, right, using gamma like this. So we have our u0 as gamma. Let me use red pen. U1 is dx by c d tau, which ultimately we can write d tau as dt by gamma. So it becomes dx by dt, which is the x component of the particle velocity. So it will become gamma by c ux. Similarly, u2 is gamma by c uy and u3 is gamma by c uz. So clubbing everything, we can write the u tilde, which is the velocity 4 vector, as gamma comma gamma by cu vector, right? This notation is simply, it's just illustrating this idea that u0 is gamma, which is here, u1 is gamma by cux, gamma by cuy, gamma by cuz, which is condensed in this u vector form, right? It is clear. So here u vector, u tilde is velocity 4 vector. Oh my god, what did I do? So u tilde is velocity 4 vector, and the u vector is the 3D velocity vector. Okay, and just simple notational clearance that c d tau can be written as ds also, where ds is the general notation for the space-time interval, and which we can see from here as well, because this c d tau square is equal to this one, and this is ds square. This quantity is ds square, the space-time interval. So dc d tau is basically ds. Very simple, right? Okay, so c d tau is equal to ds, and here we can see that because ds is space-time interval, so ds is a frame invariant or Lorentz invariant quantity, and c is anyways an invariant or constant quantity. So d tau has to be a Lorentz invariant. So it is obviously Lorentz invariant quantity. So I have covered this material in a hurry because I want to progress towards the classical field theory, which is a big topic to deal with, theory of electromagnetism and the general theory of relativity. So you can read the nitty-gritty and really, get into the details of apparent paradoxes in special relativity and get the crux of the special relativity. You should read this Space-Time Physics by Wheeler and Taylor. It is a very nice book, so you will get a lot of intuition from this book. However, we are like you can read this book for the purpose of understanding specifically the time dilation and the length contraction, which I haven't covered. Other than that, the dynamics part I will cover in great detail, so that you don't have to worry. But if you want to study about time dilation and contraction and the basic ideas, the motivation for these ideas, and the Lorentz transformation, you should definitely read the Space-Time Physics by Wheeler and Taylor. Okay, so see you next time, and next time we'll study the relativistic dynamics.